Resonance is our next characteristic of a molecule we're going to consider with regards to acidity. We've talked about resonance in introductory chemistry and at the beginning of Chem 240, and we have realized that the presence of resonance structures can help stabilize a molecule. And so if we're considering whether a molecule can be a good acid or not, we can think of whether the conjugate base has resonance structures that can stabilize it. So let's look at some common organic molecules and sort of compare their acidity. Here's methanol. It can act as an acid. Here's phenol. It can also act as an acid. And then finally, here's acetic acid. Which, guessing by its name, can act as an acid also. Okay, all these are carbon-containing molecules that have a proton that's attached to an oxygen. So at face value, they look a little bit similar, but they have very different acidities. And the difference in their acidities is mostly based on the presence of resonance structures. If we think of each of these acting as acids, we can draw out their conjugate bases. And if we have a stable conjugate base, we might imagine that the reaction of the molecule acting as an acid would be favorable. If something has an unstable conjugate base, that reaction probably isn't going to happen as often. So let's draw out the conjugate bases for each of these and see if we can give an explanation for why resonance structures might describe the relative stabilities of them. Okay, so let's start with, this is our methoxide anion, the conjugate base of methanol. Now, are there any resonance structures that we can draw for this conjugate base? No, right? I don't have any double bonds around to move. I don't have any extra lone pairs over here that can form double bonds. I'm stuck. This is the conjugate base. That negative charge is residing here on that oxygen, and it can't be spread throughout the molecule through resonance or really through induction. And so this is a relatively unstable conjugate base. Methanol is an acid, but it's a pretty weak acid, and its pKa value is about 15. Right? Similar to water. This is phenol. Okay, it can lose a proton and form phenoxide, and this can be resonance stabilized. We might imagine that some of the lone pairs can come in to form a double bond. This double bond can come out to form a lone pair, and I can draw really a set of resonance structures where the negative charge from that conjugate base now enters the ring and can be shared with the carbons in the ring. I could draw another resonance structure here showing this double bond coming over in the lone pair on this carbon or on that carbon. So there's a whole set of resonance structures available. And really what it's doing is it's spreading that extra negative charge throughout this molecule, stabilizing it. Now, our last molecule here are carboxylic acid. Is there a resonance structure that we can draw for this? Well, yeah, we've got a double bond over here. We've got some lone pairs. This lone pair could come in and form a double bond between this carbon and that oxygen. Or this bond can come out and form a negative charge on that oxygen. To form this resonance structure here. And this is a very stable set of resonance structures. While we might have more resonance structures for this phenoxide ion, here the negative charge is shared equally between two oxygens, electronegative atoms. Here the sharing is done with carbons, which are less electronegative and therefore less stable. And so while both of these acids, their conjugate base is stabilized through resonance, if we look at the pKa values, we can find that phenol has a pKa of about 10 and acetic acid of around 5. This is a better acid. The conjugate base is stabilized through resonance, and those resonance structures have the negative charge on electronegative atoms. The phenol is more acidic than methanol because it can resonance stabilize a negative charge on the oxygen.